Hello and welcome to the second topic of our talk, which will be about kernel design. In the first topic, we encountered random Fourier features, which are a way of alleviating the cubic computational complexity that GPs have by mapping the data to a randomized low-dimensional feature space and applying fast linear methods. Random Fourier features, however, do not help with the choice of kernel. Before you can apply them, you must first pick a kernel. We call the problem of choosing a kernel the problem of kernel design. A kernel can be designed by coming up with a parameterization that encodes one's assumptions about the underlying function. But this is not always easy to do, because it can be unclear how these assumptions may be encoded into a kernel, and the kernel must be a positive definite function. In the next half hour, we'll be looking at ways to very flexibly parameterize a kernel. But as I said, that can be difficult, because the kernel must be a positive definite function, and it is not clear how you can very flexibly parameterize a positive definite function. So, what else can we do? Bochner's theorem tells us that a stationary kernel is characterized by its Fourier transform, a quantity that we call the power spectral density. The power spectral density is the distribution of power contained in frequency components that make up your signal. If we were to draw a power spectral density in a graph, like this, there would be frequency in the x-axis, 0 Hz here, and say 100 Hz here. There would be power density on the y-axis, and it may look something like this. In this case, the majority of the power would be contained in the low frequency components. The only requirements that a power spectral density has to satisfy is that it must be non-negative and symmetric. These requirements are much simpler than that of the kernel, which is positive definiteness. So, if we aim to very flexibly parameterize a kernel, but we don't know how to directly flexibly parameterize a positive definite function, why don't we parameterize the power spectral density instead? We'll be looking at a number of approaches that do so. The first such approach is the spectral mixture kernel, which is a generalization of the sparse spectrum approximation that we saw in topic 1. Recall that the sparse spectrum approximation models the PSD with a symmetric average of lines, where these lines are placed at μq and minus μq to obey symmetry of the PSD. If we then inverse Fourier transform the PSD, we get the kernel associated to the sparse spectrum approximation, which is of the following form. In general, this is a pretty powerful representation. But if we only have a few lines, a few components, then that means that we assume that the underlying function is a sum of only a few sines and cosines. And that's quite a strong parametric assumption. The spectral mixture kernel alleviates this issue by instead fattening the lines and modeling the PSD with a symmetric mixture of Gaussians. That is, the PSD is now a sum of a few components where every component additionally has a weight and consists of a Gaussian bump centered at μq and one at minus μq to obey symmetry of the PSD. These bumps have widths as determined by their covariance matrices sigma q. The spectral mixture kernel generalizes the sparse spectrum approximation. Indeed, if we let the covariance matrices go to 0, then these normal distributions become direct deltas, and if we then set the weights to 1 over the number of components, we recover the power spectral density, or the form of the power spectral density assumed by the sparse spectrum approximation. If we inverse Fourier transform the PSD assumed by the spectral mixture kernel, we get the spectral mixture kernel, which is of the following form. Indeed, if we let the covariance matrix go to 0, then this exponential factor becomes 1. If we then set the weight to be 1 over q, then we recover the form of the kernel assumed by the sparse spectrum approximation. An alternative way to interpret the spectral mixture kernel is through an equivalent generative model, which is of the form of a truncated Fourier series, as shown on the slides. The spectral mixture kernel assumes that the underlying signal is of the form of a sum of q components, where every component has a weight, and consists of a linear combination of a cosine and a sine that have frequency μq, which, if you recall, are the centers of the Gaussian bumps assumed by the spectral mixture kernel. The coefficients of the cosine and the sine vary with time. They are modeled with Gaussian processes that have a kernel which is a exponentiated quadratic kernel with inverse squared length scale sigma q. What that means is the following. If a particular bump in the spectral mixture kernel looks like this and has width, say, delta f, then for the associated components, if we look at the coefficient sigma 1, the rate on which it will vary, if we look at one wiggle of this C1, say this is one wiggle, this will roughly be 1 over delta f. That is, if the bump becomes infinitely small, so delta f goes to 0, then we'll see that the rate on which C1 varies becomes very long, so the length scale of C1 becomes very long, and C1 then almost becomes constant. In the sparse spectrum approximation, there is a similar equivalent generative model, which is of a very similar form, but there the coefficients don't vary with time, so they're constant. And that means the following. The spectral mixture kernel fattens the spectral lines in the sparse spectrum approximation by allowing the coefficients in this equivalent generative model to slowly vary with time, thereby giving rise to nearby frequencies and fattening the lines. The spectral mixture kernel is a flexible drop-in replacement for standard kernels that retains simple and closed-form inference. It is able to recover many standard kernels with only a few components, say roughly 10. And finally, it is also able to model negative covariances, which is very important in, say, linear trends. However, not all is good, because in advance it is unclear how many components you need. And additionally, the parameters of these components are very difficult to optimize. The resulting optimization problem is highly non-convex and has many local minima, and the hyperparameters are super sensitive to initialization. The multi-output spectral mixture kernel generalizes the spectral mixture kernel to multiple outputs, like the name says. The construction is very similar to the single output case, with the difference that instead of Bochner's theorem, it uses a multivariate extension of Bochner's theorem called Cramer's theorem. Now that we're dealing with multiple outputs, let's denote the number of outputs by p. The power spectral density is a matrix-valued function. In particular, it is a function from the input space to the space of p by p complex matrices. Like the single output case, this multivariate power spectral density must be symmetric and it must be non-negative. And those are the only requirements it has to satisfy. Here, non-negative means that the resulting p by p matrix must be positive definite. The multi-output spectral mixture kernel models the power spectral density with a symmetric mixture of outer products of vectors of Gaussians. Now, that is quite a mouthful, so let us just pause for a sec and try to pick apart what that means and how it translates to the math below. It models the power spectral density, which is now a p by p complex matrix-valued function with a sum of q components. There, every component is a symmetric sum of outer products of a vector-valued function. Here, this function RQ is, as I said, a complex vector-valued function that takes us from the input space RD, that's D, to the space of p-dimensional complex vectors, where p is the number of outputs. Recall that if we have a complex vector A, and we multiply it by its conjugate transpose, then the result is always positive definite. Therefore, this guy is positive definite, this guy is positive definite, and so the power spectral density is positive definite. As required, that it's symmetric is also clearly the case. Every element of these vector-valued functions RQ are modeled with Gaussians like before. Additionally, they now include also a phase shift, phi I, and a time delay, theta I. Recall that a time delay, expressed as a phase shift, is a linear function in frequency. Now, if we inverse Fourier transform all of this and do a little bit of complicated algebra, as the authors did in their paper, then we get a kernel of the following form. Here, theta ij is the difference between theta I and theta j, means it's the time delay between output I and output j, and phi ij is, as you can guess, phi I minus phi j, meaning it's the phase shift between output I and output j. The other parameters, alpha, sigma ij, and mu ij, those all depend in a rather complicated way on the parameters introduced on previous slides. And if you want to see the exact expressions, I haven't put them here because these expressions are quite big. You can look at either the reader or the original paper. Yeah. Note that this thing is again of a very similar form as the spectral mixture kernel, where we have an exponential factor multiplied by a cosine. And now indeed we have a time delay added and a phase shift to the cosine. The multi-output spectral mixture kernel, like the single output case, can also be alternatively interpreted through the lens of an equivalent generative model, which again is of the form of a truncated Fourier series. In particular, it models the ith output as a sum of q components, where every component has a weight, and is of the form of a linear combination of a cosine and a sine with frequency mu q, I, where these mu's are again the centers of the Gaussian bumps that the PSD is made out of, and where the coefficients of the cosine and the sine again vary with time. Unlike the single output case, in the multi-output case, every output I has its own unique time delay and phase shift. The coefficients of these cosines and sines form together a big multi-output GP, and they have a covariance structure that's given by this formula below, which says that the one coefficients are independent from the two coefficients, and the coefficients are independent between different components, and otherwise they have a kernel that's given by this thing, which is again of the form of an exponentiated quadratic with inverse squared length scale sigma ij. Besides multiple outputs, the spectral mixture kernel can also be generalized to non-stationary signals. The authors call the resulting kernel the generalized spectral mixture kernel, abbreviated the GSMK. Their construction makes use of a non-stationary generalization of the exponentiated quadratic kernel called the Gibbs kernel. You see that it indeed somewhat resembles the exponentiated quadratic kernel here, where now the length scales depend on time, meaning that we have a non-stationary version of the EQ kernel, but we also have this weird prefactor here. The prefactor is there to ensure positive definiteness, but engineered in a way such that the variance of the Gibbs kernel is 1. That is, if we plug in t prime equals t, then we see that this prefactor, in the prefactor we have 2l squared over l squared plus l squared is 2l squared, so we get 1. Before we move to the generalized spectral mixture kernel, let us first detail a little bit how this Gibbs kernel thing comes to be. Extending the EQ kernel to non-stationary signals, unfortunately, is not as simple as making the length scales input dependent, because it then turns out that the resulting function is not positive definite anymore, and every kernel needs to be positive definite for it to be a valid kernel, so that doesn't work. To see how an extension to non-stationary signals instead can be done, let us review an alternative construction of the EQ kernel, one that proceeds by summing up infinitely many basis functions of the following form. The basis functions are Gaussian bumps centered at C and are a function of time. They have length scale L squared. They also have a particular normalization factor, which is only there to ensure that the resulting kernel will have unity variance. That's all. We then construct a generative model in the following way. First, we draw a white noise process, NT, which is a GP with direct delta kernel. Then we place one of these basis functions at every point on the real line and sum them up, all of them, by integrating against the white noise process. The resulting stochastic process, Ft, will have a kernel that's of this form, and if you then plug in the above expression for the basis function and do the algebra and the integration, then voila, out comes the EQ kernel. So now we repeat this construction, but we make the length scales of these basis functions. Recall that these basis functions can be anything. We're free to choose them. They don't have to be positive definite. We let the length scales of these basis functions depend on t. Crucially, we must let the length scales of these basis functions depend on t, not on c, otherwise it turns out that this construction doesn't work. So then we have basis functions that are non-stationary because their length scales depend on t. We again construct this generative model where we draw a white noise process, place these non-stationary basis functions at every point on the real line, and sum them up by integrating against the noise process. The resulting stochastic process will have, again, a similar expression for the kernel. And if you plug this in and perform the integration, and here you see why it's important, by the way, that we must depend on t and not on c, because this integration is over c here. So if the length scale were to depend on c, you'd have to take that into account as well. If you then plug in the above expression for the basis function and perform the integration, then out comes the Gibbs kernel in one dimension. So it is in this sense that the Gibbs kernel generalizes the EQ kernel to non-stationary signals by viewing the EQ kernel as an infinite sum of basis functions and then letting the length scales of these basis functions depend on time and seeing what comes out. The construction of the generalized spectral mixture kernel, the GSMK, is now relatively straightforward. The authors take the original spectral mixture kernel, and in there they replace the EQ kernel with its non-stationary generalization, the Gibbs kernel, this one here. They make the weights in an appropriate way dependent on time, and they make the frequencies, again in an appropriate way, dependent on time as well. The resulting kernel, it's not very difficult to verify, is indeed a positive definite function, hence a valid kernel. So now we have suddenly a bunch of unknown positive functions, the weights, the frequencies, and the length scales of the Gibbs kernels. And all of these unknown functions must be learned. So what the authors do, they give these unknown positive functions log GP priors. That suddenly turns this construction into a pretty difficult model to do inference in, because it's very difficult to propagate uncertainty through a kernel, because the resulting thing is not Gaussian anymore, so you can't compute anything anymore. So to estimate these unknown functions, they simply do map inference instead. Like the spectral mixture kernel and its multi-output generalization, also the generalized spectral mixture kernel can be alternatively interpreted through the lens of an equivalent generative model, which, like before, is of the form of a truncated Fourier series. It models the underlying function with a sum over Q components, where every component has a weight that now depends on time, importantly, and every component is of the form of a linear combination of a cosine and sine, with frequencies given by the centers of the Gaussian bumps, But now the frequencies also depend on time. And finally, the coefficients of the cosines and sines, like before, also depend on time. But they are modeled with a GP that has a non-stationary kernel, namely the non-stationary generalization of the EQ kernel. Recall that in the spectral mixture kernel case, the coefficients were modeled by simply the EQ kernel. So yeah. We have seen that the spectral mixture kernel and its multi-output and non-stationary extension assume a particular parametric model for the PSD, namely a symmetric mixture of Gaussians. Alternatively, we could use a more flexible model, a non-parametric model, meaning a model with an infinite number of parameters, by parametrizing the PSD by the modulus squares of a symmetric conjugate function h hat. So h is symmetric, well, conjugate, which means that this condition holds for all omega. Then, if we inverse Fourier transform the PSD to get the resulting kernel, we find the following expression. Here, R is the reversal function, which is simply defined in this way. Whoa, that should be a T. We therefore see that the kernel is the autocorrelation of H. This expression for the kernel can be interpreted in two ways. View the kernel as an infinitely big matrix by viewing T and T prime as the indices of this infinitely big matrix. So essentially we could interpret this. Then this multiplication here forms an outer product between H and itself, which clearly is positive definite because any outer product is. Therefore, the kernel is an infinite sum of positive definite outer products, which means that the kernel is also a positive definite function. Alternatively, interpret convolution as multiplication for functions, and interpret reversal, the R thing here, as transposition for functions. Then effectively, and this is a little bit hand-wavy, we have that the kernel is equal to H transposed, that follows from the above here. And since any outer product is positive definite, the kernel must be positive definite as well. The Gaussian process convolution model adopts this parameterization and models or gives H also a GP prior with a particular kernel, KH. But we must be a little bit careful in choosing this kernel KH. If we want the kernel, or if we want the signal modeled by this kernel here to have finite variance, then KH, the kernel here, must satisfy the following condition. Again, by interpreting KH as an infinitely big matrix, this condition can be interpreted as the requirement that KH must have finite trace. By assuming a prior over H in the previous parameterization of the kernel, the Gaussian process convolution model induces a non-parametric prior over kernels, or by Fourier transform, equivalently over power spectral densities. These priors are visualized in the figures here and here. The fat blue line is the mean of the distribution, and the gradients indicate marginal variances. One thing to point out is that the prior of the PSDs induced by the GPCM is pretty quickly decaying. The Gaussian process convolution model admits an interpretation in terms of linear systems. Since the PSD of the Gaussian process convolutional model is given by this expression here, which clearly is equal to 1 times this expression here. And 1 is the power spectral density of noise. We find that the GPCM can be interpreted as a linear system where we pass white noise here, which is modeled as a GP with a direct delta kernel, through a linear system with impulse response, H, the inverse Fourier transform of this, and then out comes the function modeled by the GPCM. Additionally, H has a GP prior, as assumed by the GPCM. This formulation, in terms of linear system, forms the basis of the inference scheme for the GPCM, but we won't discuss that here because inference turns out to be pretty involved. Alright, let's wrap up. Instead of designing the kernel, one can design the power spectral density, which has simpler requirements than the kernel. We have seen several parametric approaches. The sparse spectrum approximation parameterizes the PSD with a symmetric average of lines, whereas the spectral mixture kernel and its extensions to multiple outputs and non-stationary signals parameterize the PSD with a symmetric mixture of Gaussians. But other parameterizations are possible too. We have also seen a more flexible non-parametric approach, the Gaussian process convolutional model, which uses a cleverly transformed Gaussian process to induce a non-parametric prior over PSDs. Compared to the parametric approaches, inference then becomes a little bit complicated. Thank you.